My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I would like to welcome you all to our International Physics webinar. Good evening to all. I think you have already come to know that the Department of Physics, Pabna University of Science and Technology, has started its online program, including online International Physics webinar. And we have successfully completed our 237th International Physics webinar. Today, it's our 238th International Physics webinar. We would like to welcome you all through a joint session between our Department of Physics, Pabna University of Science and Technology, and the School of Physics, IJER, Thiruvananthapuram, Kerala, India. And we have with us here today Dr. Joy Mitra, sir, Associate Professor, School of Physics, IJER, Thiruvananthapuram, Kerala, India. And he has already connected with us. So I'd like to welcome our speaker. Sir, good evening and thanks for accepting our invitation. It's my honor and privilege to host you in our international physics.
Right. Thank you, Pretam, and thanks to the Pabna University of Science and Technology for inviting me, and Pretam, obviously. Yeah, you can hear me, Pretam? Yeah.
Yes, I can hear you.
Yeah, great. Yeah. So thank you for inviting me for this wonderful session. My name is Joy. And I am from PhysicsIISER, Indian Institute of Science, Education and Research, in a place called Thiruvananthapuram, which is the capital of a state in India. It's at the absolutely V bottom of the Indian peninsula on the Arabian Sea. And it's a picturesque place where the mountains, the Western Ghats, actually meet the Arabian Sea. And we have a beautiful campus. So today I am going to talk on the title, as you can see on the screen, is going to be Luminescence and Surface Plasmons. And so I'm going to speak on about luminescence and the role of surface plasmons in luminescence from systems. So I've given my email ID at the bottom of the page. So the students are most welcome to write to me, and others are most welcome to write to me and interact with me even after the talk and on later days. So to begin with, especially for the students, I would like to draw a distinction between a couple of words, maybe. It's a word play. The first word I would ask you to focus on is called incandescence. And now incandescence, if you actually look at any standard dictionary, Oxford Dictionary, Cambridge Dictionary, or any of the standard Webster's, this is the definition you'll actually get of incandescence. Electromagnetic radiation from a hot body as a result of its elevated temperature, especially in the visible. And incandescence is something which we have encountered all around us. And as you can see that I have a picture of a fire on the right-hand bottom corner. So the fire gives us light, and that is incandescent light. If you take a rod of a certain metal, as is shown on the left-hand picture, it's a loop of iron which has been heated. And you can pretty much see it has been heated in fire, in flame, till it actually starts glowing, and it's glowing yellow or red hot. In the center, you will see the famous black body radiation spectra, which actually shows you the intensity of the light emitted as a function of wavelength from a black body. In all these cases, what is very important for you to realize is that this radiation, this emission, comes out of is connected to the temperature of the body. Here we have radiation that is in thermal equilibrium with matter. So I'm not sure whether all of you actually understand the intensity of this statement, but I would like you to go back and think about it. What do I exactly mean by radiation in thermal equilibrium with matter? It's a reasonably heavy statement to make, but that is what incandescence is. And if you, over the last couple of centuries, as we shall see, most of our lighting, most of illumination has been through incandescence. As opposed to incandescence, there is another class of light that we actually encounter, and which is known as luminescence. Now, luminescence is very different from incandescence. And if you look at the definition of luminescence in any standard dictionary, it will tell you that luminescence deals with those phenomena of light generation which are not solely conditioned by the rise in temperature. So, therefore, you see the temperature of a body, the temperature of the body, and the equilibrium of matter and radiation is central to whether a certain source of light is incandescence or luminescence. The word lumen actually is Latin in origin, and it was first coined, as we can see in literature, if you go to the history of light, in 1888 by this German scientist and historian Elhard Wiedemann. And as we understand it today, it would be probably scientifically the definition of luminescence or a luminescent source of light would be spontaneous emission of radiation from an electronically excited species or from a vibrationally excited species, not in thermal equilibrium with its environment. And this is really the crux of the story, that you first need to distinguish between an incandescent light source and a luminescent light source. If you look at the history of light over the millions of years that we have actually spent, the universe has been in being. So you can see here that 4 billion BCE, the only source of light that the Earth, any organism on Earth would have been exposed to was the sun. And that is still the dominant source of light and energy on our planet today. And the sun is a giant black body. It's a giant black body from where it is actually radiating. It is actually radiating. And by looking at the distribution of the radiation coming out of the sun, you can the temperature of those regions of the sun, because radiation and matter is in thermal equilibrium. If you look at over the later years, you will see that humans discovered fire, or how to light fire, around 400,000 BCE, and then that fire was artificial fire or natural fire was the main source of light. Till around 500 BC, led to the discovery of oil reservoir lamps. It was absolutely revolutionary. It completely changed because now light or illumination became portable. So these are the major milestones through the human history, where light has, as you can see, played a very dominant role in actually chalking out how man's development actually came about. Around 400 BC, a candle was developed. And come to the recent history or the recent past, in 1809, led to the discovery by Humphrey Davy of the arc lamp. Then came the kerosene lamp in 1853. And that is something probably, I don't know how many of the new generation is used to, but certainly people of my generation who grew up in 1980s and 1990s, kerosene lamps were pretty ubiquitous with the phenomenal power cuts in the cities. Kerosene lamps were pretty ubiquitous, and I'm sure still many people within rural India and rural Bangladesh would be pretty, they can identify a kerosene lamp, a lantern, pretty readily. 1879 led to the development of the Edison's bulb. The first bulb actually came up, and that was a real game changer. Okay, the discovery of electricity and how electricity can be harnessed to actually give us light. 1898 came neon, which was illuminating in color now, unlike all the other sources of light, which was pretty much white or yellowish. Neon or fluorescence lights, by the time they came up, we could actually have color. If you come more forward, 1932 led to the discovery of the low pressure sodium vapor lamp, which is again pretty ubiquitous at street lighting till about a couple of years ago. Now it's slowly changing to LEDs, but till about a couple of years ago, sodium vapor lamps were absolutely all over the place. 1937, and we see the rise of fluorescent tube lights, what we call tube lights, were all over the place. Again, multicolored, a limited range of colors, but nevertheless, color was given by the active material that was fluorescing. Obviously, you also realize that since the human eye is very used to sunlight, there has always been a need of actually preparing white light sources, but colors were also fantastic. 1960 led to the discovery of, or rather invention of, lasers. 1995, the fluorescent bulb, and in 1999, finally, commercial LEDs. The LEDs were, the light emitting diodes were first discovered actually way back in 1960, but it was only after 1999 that white light LEDs became common, and that again revolutionized the way energy is consumed, the way our homes are lit, the way everything else is lit out in the commercial world. So why do we want to look at luminescence? So if we go back to this map here, the development or the history of light, you will realize that till about 1932, 1898, 1932, and in our real life, end of the last century, we were essentially reliant on incandescent light for illuminating our environment, and that was not very energy efficient. That is not very energy efficient. And since radiation and matter would be in thermal equilibrium, you had to raise the temperature of the matter to fantastically large temperatures to actually be viable light to actually come out. Whereas when it actually came to, if you look at the latter sources of light source, they want this luminescent light source. Has revolutionized today our whole entire industry. And where is luminescence useful? It's all around you. If you look at commercial illumination today, all over the place, it's essentially comes out of LEDs and the likes of it. If you look at communication technology, the displays, the LED displays, TV, your computer monitor, your flat screens, your mobiles, everything comes from luminescence. They are not really hot. You are holding a mobile in your hand. It is not really hot. If a red color is coming out, it is not red hot. Whereas, remember that picture I showed you of the red hot iron? That iron was actually red hot, and it was really hot, close to 1000 degrees centigrade before it became red hot. So here we have brilliant colors. However, it has got nothing to do with temperature. Not only applications in light and commercialization, but also luminescence has been fundamental to discovery of much more fundamental physics, particles, etc., and phenomena like the discovery of electron, X-rays, radioactivity, spectroscopy, and imaging, which is all over the place. It absolutely relies on luminescent light sources. We no longer rely on incandescent light sources. And that's where we are today. And luminescent sources are destined to play a still greater role in everyday life as we progress further into the quantum age. And this quantum age has ushered in a whole new way of communication, a whole new way of displaying things. And therefore, luminescent objects is the future. And what we are going to understand as a part of today's talk is, what is this luminescence? Where does luminescence come from? And then look in detail at a very quaint way, or a device which is luminescent. Okay, just for the sake of completeness, if you look at the Nobel Prizes which have been awarded starting from 1907 to 2014, and I have listed all the Nobel Prize which have actually gone on into areas which are very closely related to light, microscopy, spectroscopy. You can see it began in 1907 the Nobel Prize on Optical Metrology and Spectroscopy at the bottom of the page, which was given to Michelson. And then Raman got the Nobel Prize in 1930 for Raman effect. And then in 2014, Akasaki, Amano, and Nakamura were awarded the Nobel Prize for the discovery of the blue light emitting diode, which again led to the realization of white LEDs. And in between, you have the Nobel Prizes awarded for optical fibers and charge coupled devices, femtosecond spectroscopy, laser spectroscopy, lasers and masers, phase contrast microscopy, and each one of them have actually contributed immensely to our life, the way we lead our life today, and the way we comprehend nature, the way we conduct our experiments, etc. So areas which are related to light and light matter interaction is absolutely topical today and very important in our scientific world. Out of all these things, you will see that two particular discoveries, the Raman effect and the nature of colloidal solutions, these two Nobel Prizes, maybe later you will realize, is directly linked to the talk which I'm going to speak about today, and let's see how that comes about. So, speaking of luminescence, now luminescence, as I told you, is defined as light coming out without the requirement of thermal equilibrium of radiation and matter. So, what are the various sources of luminescence? So, there are some chemical sources of luminescence. Okay, and chemiluminescence can be further classified into bioluminescence, electrochemiluminescence, and lyoluminescence. And I'm going to briefly just tell you something about bioluminescence. I'm sure most of you, again, those in rural areas, not really in the cities, but rural areas, have seen fireflies. And fireflies obviously emit light. Fireflies are not alone. If you look at the sea beaches, the warm sea beaches, especially in the Arabian Sea, Juhu Beach is in Mumbai, Bombay, and that's Juhu Beach. And you can see the waves are absolutely shiny with white blue color, and that color comes from planktons. Here we have a cave, and it comes from the larvae of gnats. And here we have a Motixia millipede, which is luminescent in the night. We have earthworms, which are luminescent. We have mushrooms, which are luminescent, and we have flashlight fish, which have actually headlights just below their eyes, so that they can actually look at the prey and startle the prey and then grab it and eat it. So all these examples are examples of bioluminescence, luminescence in biological systems, and that's why it's called bioluminescence. And the core of it is a very interesting chemical reaction. It comes from a whole class of chemicals called the luciferins. And luciferins, in Latin, actually means light carrier. And in the presence of energy, ATP, oxygen, and an enzyme, luciferase, as you can see written in blue, actually creates a highly excited state of the molecule, oxyluciferin, which then decays, giving off light. So in all these, the luciferin chemical in each of these species, for the fireflies, for the planktons, for the millipedes, earthworms, mushrooms, they are all different. Different luciferin molecules are used, but the basic nature of this bioluminescent phenomena remains the same. And those of you who like, I really love a very accessible on BBC by David Attenborough, and it is called Attenborough's Life That Glows. So have a look at it. It's really a fantastic. We have other, and there is some arises material, it absorbs light and then gives out again light. And components or parts of photoluminescence that you might have come across are things like fluorescence, phosphorescence, Raman scattering, and so on. And research into photoluminescence really began pretty late. It was only in the 16th century that people started looking at natural oils, natural liquids, which were trying to give off light, a bluish tinge. Okay. Even chlorophyll is fluorescent, and it was discovered in the 19th century that if you have water mixed with chlorophyll from the plants, it actually is luminescent. It gives off its own light. And for example, this gentleman Stokes in Cambridge University, and later Becquerel, Edmund Becquerel, first detected quinine, the chemical or the drug quinine, that it is actually luminescent in the ultraviolet or just beyond the blue. So what had happened was that these gentlemen, Stokes and Becquerel, first Becquerel and much later Stokes, were holding this liquid vial filled with quinine in the blue part in the visible part of the spectra, as you can see in that small cartoon which I have drawn there. And if it is held against red light, it was red. If it is held against yellow light, it was yellow. Green light, it was green. Against the violet light, it was indigo or violet, as the case may be. And then, much by accident, they actually shifted it just beyond the blue region of the visible spectrum. So they most likely were streaming in sunlight and putting it across a prism when dispersion led to the breakup of the lights into its components. And then they were moving this vial, they were moving this small vial of quinine across the part of the spectrum, and this is how it looked. But accidentally, they moved it beyond the blue part of the spectrum. And the moment they moved it beyond the blue part of the spectrum, whence quinine was being irradiated by ultraviolet or UV light, the quinine itself started glowing bluish. And they were not even sure. This was before electromagnetic waves had been discovered, and light as an electromagnetic wave had been codified. And they were absolutely astounded that how can this liquid glow blue in a region where there is actually no colored light. There was no light because UV light is not really visible to our eyes. But anyhow, Stokes actually realized what might have been happening. He realized what might have been happening, and then he came up with Stokes' law. And Stokes' law reads that dispersed light was always of longer wavelength than the incident light. So this molecule quinine was actually absorbing the ultraviolet and actually giving off blue. And therefore, we could see it. These two gentlemen could actually see it simply because it was actually giving off luminescence. The light which was coming out was in blue, whereas it was actually absorbing in the ultraviolet. And therefore, Stokes' law always says that the emitted light comes out at a longer wavelength than the incident light or the absorbed light. So this is photoluminescence. And here is a couple of cartoons to kind of try to explain things a bit further. So, for example, what you see here is that we have a wave packet or H cross omega, some radiation incident on a system which has two electronic states. You have these red lines at the bottom and on the top. And if this radiation matches the energy difference between these two states, electrons will transit from the ground state to the higher excited state. And then what it can do is that the electron can then actually de-excite. Absorption of light can lead to electrons transiting from valence band to conduction band, and then emission of light comes as electron de-excitation from a conduction band to a valence band. Now, if there are some of you in the audience who are not very comfortable with these ideas, it doesn't really matter. Probably what you all need to understand is that the incoming radiation can actually take the electron from a lower state to a higher or an excited state, and that excited state electron can then again de-excite, giving off radiation. Just for for those who are interested in history, a bit of history of light emission, fluorescence, etc. There are these two really nice books that I have come across. The first is called Brief History of Fluorescence and Phosphorescence Before the Emergence of the Quantum Theory. And that's not really a book, it's more of a review. It was published in 2011 in Journal of Chemical Education. So you can have a look. And the second one is really a book. And the book is titled The History of Luminescence from the Earliest Times Until 1900 by Harvey. And it is published by the American Philosophical Society in 1957. Okay, both are fantastic pieces of work if you want to know a bit more about the history of light, luminescence, and so on. Just to give you a real example of photoluminescence, I have picked up something from my own research, and I do work on this class of materials called metal oxides, like zinc oxide, and they can be grown in very strange nanostructures. And you can see here scanning electron microscope pictures of zinc oxide nanorods, and here we have a luminescent spectrum. Okay, a photoluminescent spectrum of zinc oxide. And what you can see here is that on the top right-hand corner, you see there is something called lambda EXC, and lambda EXC is nothing but the excitation wavelength. So we are shining light of that wavelength. If you look at this wavelength, it is color coded for you to identify easily. When the light comes out, it's of a very different wavelength. You see, it comes out, the peak wavelength is somewhere around 370. As Stokes said that it will be blue shifted. It will be always red shifted or at longer wavelength. And 370, 380 nanometer. And then there is a huge and very shallow bump covering the entirety of the visible spectrum. But you also notice a very important thing, that the three spectra are not identical to each other. So therefore, the emission is absolutely dependent on at what wavelength the system is being excited. So it is absorbing a certain incoming radiation, and then it is giving off emission or a radiation. Okay, and the radiation, what we are trying to say is that the radiation that is coming out of the system is heavily dependent on what is the incoming radiation. More fantastic thing happens in the same system if I irradiate it at longer wavelengths, and you see what happens now. So here you have, I have now brought in other curves, emission spectra, when the system is illuminated with 380, 390, 400, and 410 nanometer of light in wavelength. And you see the emission spectra completely changes depending on what was the incoming or the excitation wavelength. So it's a fascinating area. Okay, we obviously understand and try to understand why this happens and what information it gives us about the system. And that is the interesting part of this researching these systems and working on these systems. And here there are a couple of more my initial work in this area. So there are a couple of references which actually discusses that why all these things happen and what implications they might actually have, and so on. To end my discussion on luminescence, I list the other sources of luminescence. There are various other luminescent phenomena like electroluminescence, mechanoluminescence, crystalluminescence, radioluminescence, thermoluminescence, and cryoluminescence. You are most welcome to actually search up and look at the internet and try to figure out what each of these actually mean. In fact, the movie here actually shows air bubble in water. So it is the picture of an air bubble in water, and what the people are doing is they are applying pressure on to collapse that air bubble. And look what happens when the air bubble actually collapses. It gives a brilliant flash of light. So where does that light come from? Okay, and it is an example of mechanoluminescence, specifically known as sonoluminescence, because it is to do with sound waves and pressure and so on. Okay, these are absolutely fascinating areas of study. One of the people, one of my colleagues from UCLA, University of California, Los Angeles, and this is a result from his lab. And so you can take a look at that website to figure out what's it all about. So this is about luminescence. That's where light comes out, and an emitter which is actually giving us light. But you see, color is about many other things, and surface plasmons is one way of realizing color. The most of the color that you actually come across are paints or colored or pens which are colored, which is based on pigment color. Okay, and why does the red pigment actually appear red? Because it is absorbing every other part of the white spectrum and not the red part, and that's why it kind of appears red to me. But there are other ways of creating color, and those of you, I don't know how many of you are actually exposed to things like surface plasmons, but if you can look at this cup on the bottom left hand side, it is called the Lysergus Cup, and it's in the British Museum. It's from the 4th century AD of Roman times, and it's a fantastic piece of cup, because if you look at the cup illuminated from outside in reflected light, it appears greenish yellow. If you put the light source actually in the center of the cup, then that same cup actually appears red, pink. Okay? And there are no pigments there. There are actually no pigments which are there on the cup. So how does it actually get light? If you look at the images of a painting of Monet sunrise on the top right hand corner, you see a brilliant painted picture, okay, of a sunset, of a sunrise over a lake and a boat there. So there are all kinds of shades of blue, orange, pink, green, etc., yellow. But there is not a shred of pigment in that picture at all. It is artificially constructed from aluminum nanodots. And if you actually zoom in with a scanning electron microscope deep into the surface of that picture, you will see that image E, which is these aluminum nanodots. And by changing the pitch between, or the spacing and the size of the aluminum nanodots, all these colors have actually been created. There are no pigments actually involved in this. And that goes for the other two images in the bottom also. The stained glass image from a church in France and the silver coins produced in Canada. There are no pigments, there are no paints in any of the colors that you see on this slide. So where does this color actually arise from? As I told you, I gave the answer away. The colors all arise from metal nanoparticles. The Lysergus cup is known to have gold nanoparticles and silver nanoparticles. Monet's sunrise is composed of aluminium nanoparticles. The stained glass are again composed of gold and silver nanoparticles of various shapes and sizes. And same for the silver coins, is basically silver nanoparticles on the surface of the coin of various sizes and shapes. And you can see that they have got the entire spectra of light or color actually covered. Just to prove the point that I am not joking, or this is actually possible, this is a real research image of silver nanoparticles. It's called a dark field microscopy image, and from that journal, which I have referenced at the bottom. Okay, and you can see the same silver nanoparticle of different sizes and shapes can give you brilliantly different colors. And these are the absorption spectra of these. And here you have on the top, you have suspensions, giving you fantastically brilliant colors. Different, very different colors in suspension. The bottom actually shows you gold nanoparticles, spherical gold nanoparticles of different sizes, and you can see is as you size, the color of the solution also goes on changing. So what the take home message here in this part of the story, therefore, it becomes that if you change the shape, size, and the environment of metal nanoparticles, gold, metals around you, common metals, if you change their shape and sizes and put them in solution or in an arranged fashion, they will become they will emit light or scatter light in particular things. And actually emitting light, as I have been mostly speaking of scattering light, but can they actually emit light? And let's see whether they can. So to understand that, why we have to understand some localized or nanoparticles. So they are like really small balls. Okay, the size of these balls, the diameter of these balls are tens of nanometer, even a few nanometers. Okay, so here of gold visible by naked eye. A wave on top. Suppose a wave of these balls, that an electromagnetic wave is an oscillating electric field. And in this cartoon, what is, we have a metal sphere, and those arrows denote the direction of the electric field. So depending on where the sphere is and the electric field, those polarized. They get polarized. Remember also that the electric field is the electric field, which essentially means that the polarization induced on the small nanoparticles also changes, and they go on oscillating. They go on oscillating along with the electric field. And these charge density oscillations, are the oscillations of individual nanoparticles. And if you think of it very carefully, when the electric field points downwards, you see the top of the nanoparticle will become negatively charged. Some of the nanoparticle will essentially be negatively charged. So a dipole moment is also induced. If you look at when the electric field flips, the polarization on the nanoparticle will also flip. And therefore, on each individual nanoparticle, you will actually have an oscillating dipole. And I'm not sure that how many of you actually do realize oscillating dipole radiates light. It actually gives off light. So that is one of the most fundamental parts of electromagnetism. That if you have accelerating charge, uh, spontaneously radiate dipole. Oscillating dipole is obviously accelerating because it speeds up, stops, moves in the other direction, speeds up, stops, and goes back. So this back and forth oscillation has it's an accelerating charge distribution, and these accelerating charge distributions very simply actually radiates. And so therefore you can see that these even a simple metal nanoparticle can actually radiate. But what good use is it to us? So if you actually look at that how it radiates, here is a small movie which is a calculation, and what you'll see is that how does the electric field near each of these nanoparticles behave as a function of wavelength. So we're starting from some can actually see is that a huge amount of electric field is generated on the surface of these particles. As you can see in this some of these statements that I am making, I think you can go back of me telling you, exposing you to these concepts. If you look at it spectroscopically, the image on the left actually shows you an absorption spectra. So this light is actually absorbed and then re-radiated or scattered, as in the case. It gives rise to those brilliant colors that I showed you a couple of slides back. From very simple metal nanoparticles, gold, silver, copper, aluminium nanoparticles. So if you are reasonably convinced that I can actually get light from an oscillating dipole, what you should also appreciate is that at the crux of the whole thing is the geometry and dielectric properties. Okay. If you change the geometry of the material of these balls or the dielectric properties of these balls, all these oscillations, all these induced dipole moments actually go on changing. And as they go on changing, they will absorb differently and they will also scatter or re-radiate differently. Finally, we come to the last part of our talk, and and this part of our talk is focused on this very strange luminescent source, which comes out of a scanning tunneling microscope. So again, I'm not absolutely sure what fraction of my audience today is actually very familiar with what is a scanning tunneling microscope, but I'm sure most of you are actually familiar with the concept of quantum mechanical tunneling. Okay, so here we have a very small cartoon. This cartoon is of a man and a lion who are separated by a wall, which we call the impenetrable barrier. Now, if the world was classical, then the man is absolutely safe because there is no way that lion is going to be able to jump over that barrier. The barrier is reasonably high, and the man is absolutely safe. He goes on looking at the lion through that barrier. If he can look through a peephole or something, and he can irritate the lion can jump but not affect him at all. But if the world is quantum mechanical, and that certainly seems to be the case, that classical mechanics, the classical world around us is a limit of the actual quantum world, then the man has something to worry about, because quantum mechanics tells us that even though the energy of the lion is smaller than the height of the barrier, there is always going to be a finite probability that the lion can actually tunnel through the barrier. So that a lion might not have enough kinetic energy to jump over the barrier, as in the classical case, but even though it doesn't have enough kinetic energy to jump over the barrier, it can actually tunnel through the barrier. So if you actually try to look at the wave function of the lion on the other side of the barrier, in the man's side, there is a finite probability that you will find the lion there. It will be a vanishingly small probability, but nevertheless a finite probability. And therefore, that man must run. A scanning tunneling microscope uses this phenomena of obviously not a lion tunneling through a barrier, but an electron tunneling through a barrier. And so how does it use it? What it does is that it brings a very sharp tip very close to a surface, but not touching it, such that there is that barrier, and then applies a bias. Now, if it is not touching it, the electrons are not supposed to flow from the tip to the sample or the material below. But what actually happens is, due to this quantum mechanical tunnel effect, some electrons can actually tunnel through the vacuum or the separation between the tip and the substrate below, and jump from one to the other, and vice versa. And this phenomena of quantum mechanical tunneling has been used mostly to do topography or imaging nanoscale objects. Here I have an array of images from my own research experience, and you can see gold nanoparticles, beautiful structure of a gold 111 surface, the structure of silicon at various voltages, of graphite, and you can see really the hexagonal structure of graphite, self-assembled monolayers of cadmium selenide, all from my own research work, and also much more exotic things copper, and even today, the tunneling microscopy can be used in some form or the other to actually image the molecular orbitals of organic molecules like pentacene that is actually seen on the screen. So apart from actually giving you the topography of surfaces by using this very strange quantum mechanical tunneling phenomena, if you actually try to look at if whether light is coming out from this tip and sample junction, and you will see that you will actually get light. So you can have a metal tip on a metal sample, and you apply a DC bias, and electrons flow from one to the other, dependent on the direction of the bias using quantum mechanical tunneling. But as a byproduct, it actually gives you light. So how do we detect this light? As you can see here, in the diagram, here I have the tip, and here below I actually have the sample. Okay, and I bring the tip very close to it, and electrons flow from the tip to the sample or the sample to the tip, depending on the direction of the bias. And what I do here is that I have a couple of lenses. Here and an optical fiber. So this lenses and optical fiber are positioned very close to this tip and sample, typically a few millimeters away, and it can capture all the light that is actually coming out from this region. And then it is fed into a spectrograph, and with a CCD camera, a charge coupled device camera, and then we can actually actually detect the light. Okay. So what do we actually see? We can, apart from the light, we can actually see the photon maps, and you can see here the surface of a polycrystalline film of gold, a topographic, and simultaneously acquired a photon map. This is actually light coming out from these gold islands. This is a single crystalline, and you can see again on the topographic map, the light or the photon map. Light is coming out from this junction and the tunneling electrons. And here we have a whole range of more exotic systems where when the STM tip is taken onto these molecules, these nanoparticles, etc., we have light coming out from all these material systems. And it's really rather fantastic. And this was discovered only in the 1980s. So it is just 20 or 30 years ago that this whole phenomena was discovered, and it led to a whole new area of research in luminescence. Apart from photon maps, we can also nanometers to 1,000, 1,200 nanometers. And much of my research actually goes into understanding why this light comes out and how can we control this light. Now, this is really a fantastic light source. The physical dimension of the light source is in the nanoscale. So this very small, tiny light source gives off light brilliantly, and it carries information about the local material of the system. As I showed you in the previous in these photon maps, as you can see, the light coming out from the system in trying to investigate the physics and chemistry of nanostructures. So in order to understand that, how that light actually comes out, probably I'll paint a very simple picture. So here I actually have the STM tip, okay, and this part on the top is the STM tip, and below I have the sample. And what happens is we apply a bias between these two, and we have a current. We have a tunnel current. Now the bias applied is a DC bias. The bias applied is a DC bias, and one would expect that the current, the ensuing current, is also a DC current. But that's not what happens. If you actually look at the time series of the current, you will see that that current is extremely noisy. The current obviously has a mean or DC part, but it also has an oscillatory or AC part. And this AC part essentially are fluctuations. So if you actually model the charge distribution in the junction, you will see that there are these fluctuations or oscillations at the tip end and just below on the sample between the tip sample junction. And as these charge densities oscillate, you notice these are obviously calculations. We can't really measure them. But you see, it is like a dipole. The blue represents the negative charge and the red represents the positive charge. And you see they go on oscillating between the tip and the sample, reversing themselves just like an oscillatory dipole. And this oscillatory dipole then again radiates to give off light. And therefore, the oscillations are absolutely dependent on the local geometry and material properties of the system. And this simple model basically tries to show you or tries to convince you that indeed light can come out of a very this strange junction or an STM junction. Okay, and obviously there are more sophisticated physical phenomena or phenomenological models in terms of which we actually discuss or model these. And so what we start off is by these coherent charge oscillations, and then we go to these oscillating dipoles in terms of which we define the radiation. And these are mediated by what we call the localized surface plasmons and the surface plasmon polaritons. So there is a huge quantum picture various model a very large degree, the phenomena, semi-classical modeling, a bit of quantum mechanics, a bit of classical physics. We can put it together, and then we try to understand to a large extent why the emission comes and how one can control it. So, for example, these two panels on the right hand side, the top is an experimental spectra, and the bottom is a calculated spectra based on a phenomenological model that we have actually developed. And you can see that some of them we understand them very well, how to control it. But there are some other features which we don't understand, some properties which we don't understand, and which are under active investigation. We also do understand that shape or the geometry of the system is of vital importance. And you can see here 3 spectra of the emitted light, and which is absolutely dependent on the shape of the tip. If you have a sharp tip, a mediumly blunt, and absolutely blunt, 10 nanometer, 25 nanometer, 80 nanometer, 3 tips, they give off a very different light and a very different spectra. And therefore, as I said, that we understand some parts of it, and there are some parts of it which we don't. As I told, I've been trying to repeat that all these phenomena depends on the dielectric properties of the systems. So whether it is gold or silver or copper or aluminum, it is going to change. It changes with the geometry of the system. These luminescent properties changes with the geometry of the system. Am I using a sharp tip or a spherical tip or a hexagonal tip? It changes with that. But more importantly, it also changes with the environment. So in an experiment which we did around 10 years back, what we had shown was that if you actually change the local dielectric environment, like by introducing water into the junction, the spectra or the emission again changes. And this is again a very powerful technique then, because then it allows us to measure the dielectric properties of molecules and materials around the junction. And it's a precursor to an ideal dark field spectroscopic technique, where the dielectric properties of the environment actually influence the light coming out of a tip sample junction. So I will skip these details, and I'll probably come to and try to tell you quantum mechanically how does one comprehend such a light emission. So if you actually look at a tip sample junction, those of you who are familiar with the concept of Fermi level or Fermi energy will appreciate that any material system, one second, any material system, in any material system or a metal, electrons are filled up to the Fermi level, which is EF. And at finite temperature, there is a certain spillover at energies beyond, but mostly it's filled up to the Fermi level. And so if you bring this and the sample by tunneling, by quantum mechanical tunneling, one of the properties of quantum mechanical tunneling is that it hardly loses any energy. And this kind of tunneling is known as ballistic tunneling or elastic transport. It doesn't lose energy. Okay. So therefore, an electron from the tip moves to the sample, however, it doesn't lose any energy. And when it goes to the sample, it couples to the phonons and thermalizes. Whereas in the phenomena that we are studying, what happens is that when the electron moves from the tip to the sample through the barrier or that impenetrable barrier, what it actually does is it couples onto background phonons of the vacuum, photons of the vacuum. And these photons are then scatter the electrons. The electron loses its energy and gives off this photon, which is emitted as light. And this is the quantum mechanical picture that we are trying to comprehend still. There are probably some 5-6 groups all across the world who are trying to comprehend how this coupling takes place between a photon and a tunneling electron. And we have made some progress, but there are many unknown which is still left. Just to show you that how these charge oscillations can actually be visualized, our theoretical calculations, which go hand in hand with the experiments, visualize charge oscillations at the junction like this. And you can see the charges if you actually put in the theoretical models that we have come up with. This is how the charges actually oscillate at the tip sample junction. And as these charges oscillate, it goes on radiating light, which is then evidenced in the photon maps or the spectra that I showed you earlier. So this whole thing, the whole concept of luminescence and plasmonics and surface plasmons has a lot of applications. Localized plasmons, it's absolutely being used in research, not only in research, but also in applications in the semiconductor industry and in spectroscopy. I'm sure you have heard of plasmonic nanosensors, which are today used routinely in biological labs to detect bindings of proteins and biomolecules, to detect reaction and binding kinetics of biomolecules. And luminescence associated with plasmonics is a fascinating area which we research, and is being researched very actively by chemists, biologists, physicists. It's an absolutely interdisciplinary area with a huge potential. Okay, and yeah. So again, before I leave you, these are some of the major take homes from the area of plasmonics, and especially light emission or light manipulation that is afforded by plasmonics. Yeah, so that kind of brings me to the end of my talk. And before I end my talk, it's also customary to thank all my collaborators and financiers who actually allow me to who fund my research and who allow me to do these very interesting things. And these are my collaborators from all over the world, really, mostly in Singapore, UK, Europe, and obviously my students from IISER, who actually do all this work so that I can talk. to the audience. So a big thanks to all of them and all the financials who are outlined below. This slide the various research interests which I have, mostly on plasmonics, optoelectronics of oxide semiconductors, applications of junction devices, and various other biological systems. And these are some of my publications in the more recent years in each of these areas. So if you people are interested, you can go to my web page, and this is my web page there. My email is also there, and my web page is also there. So if you are interested, do write to me, and so I can open it up for questions now.
Yeah, thank you, sir, for your wonderful and exciting presentation, sir. So we have few questions in the comment section, and we have a guest with us. So I can add. So Shubho Mitra, can you hear us? So thanks for joining with us. So you can ask
Yeah, I
question
can
if
hear
you
you.
have question.
Yeah, yeah. Sir, I'm also a fellow Iserian from Iser Mohali. I just get from the Facebook that there is a link talk going of
Yeah,
Jai sir.
thanks.
So it's a very nice talk. Just a basic question like we are talking about surface plasmon. I just got disconnected on at that time. So I just
Okay.
want to get some connection. Like you showed during the photoluminescence, and then you
Yeah.
enter to the surface plasmon thing. So
Mhm.
can you just
Mhm.
repeat that part? How I mean, how the things move to the surface plasmon one? I mean, all the things are using on the matter of light matter interaction. But
Yeah,
I just
exactly.
want to
So
correlate that thing.
right. Okay. So obviously, as you saw in the case of photoluminescence, that part was more on the various the various facets of luminescence per se, and photoluminescence obviously is to do with you shine in light. It's a very general term. Okay. So therefore, you shine in light, and a
Yeah,
different light comes out as given by Stokes law. Okay. And as I tried to show through the
yeah,
semiconductors, that you can comprehend a certain way in terms of the band picture or the electronic state picture, that why certain lights of a longer wavelength will actually come out. Okay. But it is not so simple when you actually move to
yeah,
a non band gap system like a metal. Okay. In case of a metal, there are no electronic transitions. There are obviously electronic transitions which are happening, but there are no forbidden band gaps such that they should naturally emit light. They have no other way of de-exciting the part to
okay. They
emit
are
light.
overlapped.
That's why,
Yeah,
yeah, they are all overlapped. So therefore, at that stage, if you try to
yeah,
look at re-radiation or light emission, you have to look at, one of the models that we look at is this dipolar radiation. Okay, where an induced dipole kind of oscillates. Okay, it accelerates, and it's an accelerating charge system, and therefore it can scatter, it can re-radiate, it can luminescent, it can actually give out these colors. Okay, but at the end of the day, it can do all of
yeah.
this in the presence of an incoming radiation. Okay, so therefore, to that extent, they are all still
Okay,
photoluminescence. Do you understand? Okay, without that incoming radiation,
okay,
they
okay,
are not
okay,
able
okay.
to give out light. Okay, whereas when I go to the STM,
Yeah, yeah, yeah,
as I try to say, there is no incoming light. It's a dark field, right?
yeah, yeah. Okay.
There is no
Yeah, yeah. Got
incoming
it.
light. These are oscillations as fluctuations themselves. So did you
Yeah,
get that, Shu? Yeah,
right.
yeah.
Yeah, yeah, sir. Correctly. Sir, and one more thing, very basic questions from photoluminescence, like fluorescence or phosphorescence. Like phosphorescence
Mhm,
is a longer time phenomena than fluorescence. So,
mhm.
can we comprehend this thing in the surface plasmon or scanning tunneling microscopy thing? Like in the phosphorescence, we we measure the emission spectrum. at the together we cannot get the phosphorescence, right? Like in a
Sorry,
can we measure
sorry.
that? I mean,
Repeat your question.
just out of curiosity.
No, can you just
Yes, sir. Like you measured the fluorescence, like emissions. Hello.
hello? Yeah, tell me, Shubha.
Actually, it's getting this. Yeah,
It's getting
just
disconnected.
a
Yeah.
question out of curiosity. Like you, yeah, yeah. Can you hear me now?
I can hear you actually.
Yes, we can hear you. You can.
Okay, fine. Yeah. So the question is very basic. Like you have taken many photoluminescence spectra for your
Mm-hmm.
different samples. Okay.
Mm-hmm.
So I just want to know, I what I know, like it's very difficult to get like fluorescence and the phosphorescence spectra together. It cannot actually, right?
See, the question is of lifetimes to a large extent between a phosphorescent and a fluorescence. Okay, phosphorescence will
Yeah.
essentially have a fantastic
So
large lifetime. Yeah. Mhm.
yeah, it's around microsecond.
Yeah, I
So
mean,
is it
even
possible? I
longer.
mean, so do we get
Huh.
the okay. So I mean, can we disentangle those two spectra between a particular signal? Like it should come, like
Um,
because it's a longer time phenomena.
yeah. Yeah. So yeah. In principle, yes. So it's basically it goes into a metastable state, and depending on your detector.
Yeah,
Okay, it depends on your detector whether the detector can discriminate
yeah,
between these two signals without kind of saturating itself. Yeah. So it's more of a technical problem rather than a science
yeah.
problem, that whether you can actually discriminate between
Ah,
these. Yeah.
okay.
Yeah.
Okay, sir. And sir, last one
Okay.
thing, like you showed the dark field microscopy of Ag
Mhm.
atom, I think. So
Mhm. No,
there
it's
I
not an atom,
found
it's
the
these
different
small
colors
nanoparticles.
are scattering. So that depends. Yeah, sorry, nanoparticles. So they are different colors scattering from that particle. So that depends totally on the size of the particle, right?
It depends on the
Like
size
how
of the
you
particle.
impinge
It
on the
depends
surface.
on the dielectric function of the particle. For example, whether it is gold, silver, or copper or aluminium. Okay, so that dielectric function. In case you
Okay,
are,
sir.
I don't
Okay.
know what is your advancement, Shubha. In case you know about the Drude model, the plasma frequency,
Yeah,
etc. So the electron density,
sir. Actually,
anything.
I do laser spectroscopy. So
Oh, right. Okay. So therefore,
yeah.
if you are familiar, well, the simple
So
root model
yeah,
of metals, the AC conductivity, that's probably the easiest to understand. And
yeah.
there is one parameter which controls it, which is the
Yeah,
plasma
yeah.
frequency, dependent on the number density and the effective mass
Okay.
of
Yeah.
the electrons in the system. Okay. So these two parameters that's the easiest way to comprehend it.
Okay.
It may not be the full picture, but it's most the easiest way. So those two parameters will probably decide the optical properties of the metals, and so therefore it is the geometry, is the optical properties
Okay,
of
sir.
the metals and the environment.
All right. Thank you, sir. Thank you very much. I got it. Yeah.
No
Okay.
problem.
Thank you, Shubho, for joining with us. So we have a
Yes.
few questions in comments.
Thank you,
So
Pretam, sir.
Yeah.
okay. So can a neutrino passing through a conductor or semiconductor can emit a single plasmon into the medium?
A neutrino. Yeah, well, my knowledge of neutrinos are rather weak. Okay. So I suppose yeah. So yeah. Okay. So the neutrino, the energy of a neutrino. Okay. Yeah. I mean. Okay. So a plasmon. Okay. Let me put it this way. So a plasmon is a collective charge oscillation. Okay. It's not a single electron oscillation. Unlike what happens in photoluminescence, these are not single electrons which kind of move from one energy state to the other, but these are collective electron oscillations. And therefore, any excitation which can excite electrons collectively can actually excite the plasmons. So if the neutrino has a characteristic energy which can excite the collective charge oscillation modes, or the free electron oscillation modes of the system, then yes, it will. So light can do it, electrons themselves can do it, as I showed you. Okay, so if light can do it, electrons themselves can do it. There will be other excitations, other ions or fundamental particles which can actually couple onto electrons. Okay, so I wouldn't, I don't know a direct example, or I never have come across it. But if there is a scattering cross sections of neutrino indirectly affecting electrons, not directly obviously, then yes.
Okay, so thank you. We have another questions. So, how do the neutrino emission due to plasmon decay leads to the neutrino luminosity of white dwarfs?
No, I don't think so.
Okay, so this may be the last question. So, do the nonlinear nano optics of the surface plasmons, polarization, polaritrons of the Planck scale exhibit the effects similar to the well-known effect of quantum gravitational theory?
Okay. Again, let me try to understand. Do the nonlinear nano optics of the surface plasmon polaritrons at the Planck scale, you actually mean the Planck scale, the fundamental Planck scale, exhibit effects similar to the well-known effects of quantum gravity? I mean, the well-known effects of quantum gravitational, to my best of my understanding, there is no quantum gravitational theory. Okay, so I am not very sure. Abhinav, I mean, able to answer it at all. Okay, the nonlinear nano optics of surface plasmons is something which is very.
So, can you hear me? Okay, so as we don't have any more questions, we can conclude our discussion session. So thanks, sir, for your nice presentation and discussion session. So we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation. Bye for today.